Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to module 7, the module 1 of this course on machine learning for earth system science, which is on spatio-temporal statistics. Today is the lecture 7 of this module, and today we are going to deal with extreme value theory. So, if you remember, in the previous lecture we had already been discussing about extreme values of geophysical variables like the precipitation and temperature and so on. We had defined quantiles and things like that, and how to define extreme events in terms of such quantiles. Now today we will learn a few more concepts: probabilistic estimation of return levels and return periods. So, return levels and return periods are concepts which we had already studied in the previous lecture. Today we will see how to estimate them from using probability distributions. And the second thing which we will learn today is generalized extreme value distribution. So, first of all, let us just come back to extreme event definitions. So, in the previous lecture we had considered setting some kind of threshold on the value of the geophysical variable, or rather on the anomaly. If the anomaly is above certain threshold, we will call it as a as a positive extreme, and if it is below certain negative threshold, then we can call it a negative extreme. So, this kind of definition is sometimes known as the peak over threshold definition of extreme events. So, like where an observation with a high, like where the magnitude of the anomaly is high, and like if we are plotting the time series of the variable, then the extreme events which we are talking about, they also usually correspond to peaks or troughs of the time series, like that I mean, which are like either higher than their neighbors or higher than some threshold. So, in a sense it is like a local and global maxima or minima. Now, the thresholds which we are talking about, those thresholds can be either like absolute, like say something like mu plus 2 sigma, or it can be in terms of actually it can be some like above some fixed value, or it can be like something like mu plus 2 sigma, or it can be in terms of these quantiles. So, like for example, the 90th, 95th or 99th percentiles. There is a different definition of extreme events also, that is of the block maxima or minima. So, this approach is that instead of considering individual observations, we consider sets of observations and calculate their maxima or minima depending on the kind of extremes we are looking for, positive or negative. And this set of observations, it can either be a spatial set or a temporal set. That is, either we can consider the observations over like a certain period of time or over a certain number of locations. When we are dealing with blockwise extremes, in this case, say for example, we consider the seasonal maximum precipitation over Kharagpur. So, in that case, instead of dealing with all the observations, we now deal with only the maximum values. That is to say, in any given year, we consider we do not consider the values of daily rainfall. Instead, we for every year we keep just one value, which is the maximum daily rainfall in that year. Of course, it need not be, the blocks which we are defining need not correspond to years, they could also correspond to months, weeks or anything like that. But like in this example we are considering years. So, the advantage that this approach has is that there is less variance. Like if we are considering data, the variance will be much higher, because there will be many days in which precipitation will be absent totally, that is completely dry days, and there can also be days of say where there is some 150 millimeter of rainfall or so on. In the previous lecture, if you remember the time series of 15 years that we considered, there was one day in 2007 where some 152 millimeters of rainfall had been recorded. So that shows how much that the variance can be if we are dealing with daily data. But if we deal with only block wise data, such variance is significantly reduced, and in fact larger is the block size, the smaller we can expect the variance to be. However, the problem with this approach is that there is considerably less data. That is, instead of having in 15 years, we can have 1830 data points if we are going for daily data, but if we are going for annual maxima, then for 15 years we will have only 15 data points. So, that is a significant reduction of these data points. As a result, any statistical quantity which we may want to estimate, they will be, such estimates will be increasingly less robust. Okay. Now, also the distribution of these values will also significantly change if we consider the extreme values or these block maxima only, instead of considering all the daily values. So, this is actually the block maxima time series of rainfall over Kharagpur for 118 years from 1900 to 2018. So, it is like in every year we are just recording the maximum rainfall that was recorded on any day of that year. Like say in this year, for example, there later maybe this is 1924 or something like that. So, here we see that the day with the maximum rainfall had only about 50 millimeters of rainfall, while in this year, which might be say 1956 or 57 something like that, in this year there was one day in which there was at least 290 millimeters of rainfall. So, that amount of deviation is there. However, we can still say that the variance of this time series may be less than the variance of the daily time series which we saw in the other day. Now, based on this time series of annual maxima of daily precipitation, now I am asking you one question: what is the return period of an annual maxima of 150 millimeter? That is, say on any given day in any given year, let us say there was a day in which the rainfall was 150 millimeter. So, what is the probability or what is the expected number of years after which this kind of thing will happen again? So, if you empirically look at this time series, you will see that there are a number of years where the maxima has exceeded 150 millimeter, like for example this year, this year, this year, this year, etc. In fact, if there are 20 years in this period, in this 118 year period, in which the annual maxima has been 150 millimeters or more. So, when I am talking about annual maxima of 150 millimeter in the context of extreme values or these return values, we do not mean specifically 150 millimeters. We always mean 150 millimeter or more. Even though we do not write the or more part, you can consider it as implicit. Now, how to estimate these kinds of return periods? So, in the last lecture, what we were doing is we are trying to do empirically. We were simply for example, we were for some particular values, we calculated the number of days in which the rainfall had exceeded that value in that 1830 year period, 1830 day period, and accordingly we were setting its various percentiles, like this is 99th percentile, that is 90th percentile, and so on. But that kind of analysis we can do only if we have a lot of data. That is, like 1830 we can say is a reasonably large number of data points, but in this case, as you can see, the number of data points is significantly less, only 118 data points are there. So, the more now the error here scales with the square root of the number of data points. So, as we want to reduce the error, we need to increase the number of data points quite significantly. So what happens is that if we in this kind of a situation where we are dealing with these block maxima, hence we have significantly less data, going for by the empirical method of just counting how many times this event has happened in this period and just taking the inverse ratio of that is usually not a great idea. Because as I said, the data is not enough to make a statistically significant or statistically robust estimate like that. So what do? The answer is that we try to fit probability distributions. We fit some kind of a distribution on the quantity of interest and then find the probability of the specific event that we are interested in, which may be that the daily rainfall exceeding some peak or the annual block maxima exceeding some peak or something like that. Okay. So the basic idea is that we fit a probability distribution on the observed values. Now the distribution PDF that should reflect the histogram of the observations, and then the parameters may be of the distribution, they may be estimated using maximum likelihood or Bayesian estimation or something like that. So whichever probability distribution we are fitting, be they Gaussian distribution or gamma distribution or Bernoulli or whatever, it will have its own set of parameters which need to be estimated, and that is parameter estimation will be done from the data itself. So there are certain standard approaches for estimation of these parameters. The most well known is the maximum likelihood estimate. So while I leave it for to you as a homework exercise to read more about how exactly maximum likelihood estimate is done, in case you do not know it already, I will just give you the basic outline. So the idea is that as we know, every distribution is associated with certain parameters. So what we need is, we need to choose the parameter values such that they fit the observations well. Note that we do not have the probability distribution to start with. What we have is only the observations. Now we have to imagine the observations to be realizations of some random variables and then fit an appropriate probability distribution to that random variable. Now choosing a probability distribution means two things. One is to choose the family of the distribution, is it Gaussian or gamma or whatever, and the second is to estimate the values of the parameters. So for the second purpose, what we do is we write the joint distribution of all the observations by treating them as IID, and then this joint distribution is called the likelihood function of the parameters. So note that when we are writing this joint distribution of all the observations, this such a joint distribution will include the values of the observations as well as the various parameters, but while the values are known because they are observed, the parameters are so far not known, we are trying to estimate them. So they are the variables of this joint distribution which we are writing. So we call that joint distribution as the likelihood function of the parameters. And now we will choose the parameters in such a way so as to maximize this likelihood function. So we can write, once we have the function in terms of those parameters, we can just use something like we can write the partial derivative with respect to each of the parameters, equate those to 0, we will get some simultaneous equations which we solve and get the estimates of the parameters. So this is called the maximum likelihood estimate. Now in this case, when the aim is to estimate the return value of the return period of 150 millimeters of rainfall. So first of all what we do is we plot the observations. So for the time being, forget about the block maxima part. Let us say we are just dealing with the daily rainfall values. So we now let us so if we plot their histogram, this is what that histogram looks like. So you can see that the low values have very high probability and the high values have increasingly lesser and lesser probability. Now this this is the PDF. Now whatever if we want to imagine that these observations are actually realizations of some random variables, we should choose such a distribution whose PDF is approximately has this kind of shape. So, what comes to mind is the gamma distribution. So, the like we know that the gamma distribution has this kind of step, that like as you can see, this is a typical PDF of a gamma distribution. You can see the similarity between these two curves, and it is like usually gamma in the literature, gamma distribution is considered as a good as a suitable distribution for this daily rainfall. The only catch is that gamma distribution is not defined for for zero values. That is, the support of the gamma distribution is like 0 to positive infinity, but specifically the point 0 is like the PDF is undefined at the point 0. So, what we will do is we will like consider only the wet days, that is where the rainfall is non-zero. We will estimate the parameter, like that is we will fit this kind of a distribution, the gamma distribution, to only the wet days where there is non-zero amount of rainfall. So, like you can say that the amount of rainfall on any given day will be modeled as follows. On like first we will choose whether it is a dry day or a wet day. If it is a dry day, then the rainfall amount is automatically 0, and if it is a wet day, then the amount of rainfall we say it follows the gamma distribution. Okay. So, like by focusing the gamma distribution only on the wet days, we calculate the maximum likelihood estimates of the gamma parameters as these two, 0.62 and 18.98. So, like the gamma distribution, it has two parameters, the shape and scale parameters. So, like these are the values which we estimate from the data by maximum likelihood. Now, so using this gamma distribution, let us do the mathematics and try to estimate that return the return period of 150 millimeters. So, first of all, like when we are talking about the annual maxima in a particular year is 150 millimeters, what that means is that there is at least one day in that year where there has been more than 150 millimeters of rainfall, right. So, the probability of such an event is of course the complement of the event that every single day has a rainfall of less than 150 millimeters. Now, it is the second thing that we will try to calculate using the distribution above. So, the event that every day's rainfall is less than 150 millimeters, this can be decomposed into that is one day's rainfall less than 150 millimeters and raised to the power of the number of days. That is, every day we treat as independently, so that this joint distribution, it just becomes the probability of the individual distributions, that is the probabilities for each and every day. So, remember that there are 122 days only in the season. So, what we so what we need to write is the probability of a rainfall in a particular day is less is less than 150 millimeters, right. So, sorry for the typo here, this will be 150 not 0. So, now this the probability that the rainfall on any given day is like above 150 millimeter, that can be calculated using this kind of a gamma distribution as follows. The probability, so first of all the gamma distribution is, remember that the gamma distribution is talking only about the wet days where there is non-zero rainfall. So, the gamma distribution gives us this probability, that the probability on any given day the rainfall is above 150 millimeter, given that it is a wet day, okay, and that probability comes out to be 0.0001. That is, if you simply plug in these parameters to the gamma PDF, this is the value which you will get. So, I leave it as a homework exercise for you to do this calculation once again. So, you can do it in MATLAB or Python, there are well known libraries for that. You do not have to write any function, you just have to there is just one function which you need to call and provide it with these parameter values, and it will give you this probability. Now the probability of a dry day that turns out a probability of a wet day that turns out to be 0.81. That means of the 18th of the days that we considered during this period, whatever is the number of days, that is 81% of them are wet, that is the rainfall is non-zero. Only 19% are completely dry days. So the probability that on any day the rainfall is above 150 millimeters is this times this, right, and then so what we the probability that any day's rainfall is less than 150 millimeter will of course be 1 minus that quantity, right, and then so we calculate the 1 minus that quantity and then raise it to the power of 122 coming because there are 122 days in every year from June to September. And after doing this calculation, the value, the probability value we get is this thing 0.0098. Again you should cross check these calculations. So that means what? That means the probability that in any given year there will be the annual maximum will be more than 150 millimeters turns out to be 0.0098 according to this model, which is based on a gamma distribution on the daily rainfall amounts. Now based on this, if you want to calculate the return period, this will be like as we saw in the last day's last lecture, that is just the reciprocal of this probability, which and it turns out to be 102 years. That means this kind of an event will recur after 102 years each, that is nearly 100 years. But here in this case we are considering 118 years of data, right. Now so within that 118 years, if the return period is 102 years, then of course in that period the expected frequency of this kind of an event, that is annual maxima exceeding 150 millimeter, this will happen just once, right. But if you consider the actual data which we have, that thing is such an event actually is found to happen at no less than 20 times. So the model's prediction is horribly off the mark. It has said that this kind of event will happen only once, but it is found to be happening 20 times. Which so if we the problem lies in the quantiles of the distribution which we just fitted, namely the gamma distribution. So if you consider the QQ plot between, so these are the actual observed observations of the daily rainfall over that period, and these are the samples drawn from the distribution which we just constructed. The gamma we fitted the gamma distribution with those estimated parameter values. So if you see the QQ, the idea, like if the two distributions are perfectly in sync with each other, or rather if the fitted distribution perfectly matches the data, then we expect the quantiles to follow this this line. But if we find that the plot follows this line only for only for a certain period, after that we find or rather only for low values both are matching. After that we find that like the fitted values, they are they just fall off the mark, that is let us say this 200 millimeters. So like this 200 millimeters may have a certain quantile according to the fitted distribution. Let us say it is the 90th percentile or something like that, or 95th percentile maybe. But the corresponding percentile in the fitted distribution, which the 95th percentile, is only about 100 millimeters. So we and for the even higher values like say 250 millimeter and so on, we see it's like the same case only. So that means the probability distribution which we just fitted is unlikely to predict the kind of high values or extreme values which are actually observed. Okay. So that means what? That means the probability distribution that we fitted, the gamma distribution, it fits the lower values quite well, but the higher values it is not able to fit. So like what is the need of the hour is to have a separate distribution only for the high values, which are known as the tail of the distribution, and this is where the extreme value theory comes in. Now this so in extreme value theory we focus only on the tail of the distribution, and this distribution is usually very different from the original distribution. The original distribution is often very much skewed on one side. Like if you see like the original distribution of daily rainfall, it looks somewhat like this, but if you consider something like a block maxima, that is what like we may see a very different distribution. So if you like in this specific case for those 118 years, if you consider the block maxima of annual rainfall, and like if you calculate the histogram of that, this is what that histogram looks like, which as you can understand is very different from the histogram of daily rainfall which we got here. You can so you can see this is very much left skewed. This on the contrary is not quite like that. And this is the here what I am showing here is the CDF of that of the corresponding quantity. So now what we are going to do is we are going to suggest a new distribution which is specifically meant for this block maxima. This is known as the generalized extreme value distribution. So let us say that this x is the block, or let us say that this quantity mn, this like m is stands for some particular variable of interest and n stands for the block size. So what we are saying is that the probability that the the maxima of a block of size m is less than equal to x follows this kind of a distribution. So this generalized extreme value distribution is derived, this expression of this PDF is derived in a certain way, that is starting from the individuals or assuming some kind of an exponential distribution on the individual observations, we come to an asymptotically we come to this kind of a distribution over the maxima of a block of distributions, and this is what that distribution looks like. So here you can see that there are basically three parameters, the mu, sigma and this xi. So the once again these are like they are the location, shape and scale parameters. The mu is called the location parameters, and this sigma is the scale parameter. So now what we can do is what we can do is when we have a set of observations, we can actually normalize them in a certain way, so that this mu becomes equal to 0 and this sigma becomes equal to 1. This is not identical but analogous to the case where we have a normal distribution and we just generalize it and bring it to the standard normal distribution which has mean 0 and variance 1. Now the more interesting thing is this quantity xi. This is in a sense it is like the shape of the distribution. So if this xi parameters is negative, then that specific case is called the Weibull distribution, whose PDF you can see here. So as you can see, this is actually a bounded maxima, that is beyond a particular value there is a fixed value above which there is 0 probability of occurrence. Then there is, if xi is equal to 0, then this is what is known as the Gumbel distribution. So it is this that red curve. So this is a situation where it asymptotically goes to when the PDF asymptotically goes to 0. That is like as we go to higher and higher values, this the PDF becomes smaller and smaller and ultimately converges to 0 in the limit. And the last case, the black curve where xi is greater than 0, that is called the Frechet distribution. So here this is called the heavy tail distribution, where even the very high values of these block maxima, they continue to have a reasonable probability. Okay. So now as I said, these three things, the location, shape and scale parameters are the parameters of this generalized extreme value distribution. So just like in the previous case, here also we can estimate those parameters using the maximum likelihood estimate, and here these are the maximum likelihood estimates which we have got in this particular data set, the 118 year data set. So, according to this distribution, once we have fitted these parameters, we can calculate the probability that the annual maxima is going to exceed 150 millimeter, and that probability turns out to be 0.14, and its return period is then just the reciprocal of 0.14, which is about 7 years. That means the expected frequency of this event, that is annual maxima exceeding 150 millimeter, the expected frequency of such an event in 118 years is 118 by 7, which is 17. Okay, so we can expect that in the 118 year period such an event will happen around 17 times, while the observed frequency is 20 times, which is actually pretty much matching. Now compare it to the previous case of the gamma distribution on the daily values, where we had got which had predicted only once. So, from once we have come to 17 times. Of course, 17 times is still lesser than 20 times, but compared to what we have earlier, now we are doing much better. And if you consider the QQ plot now, like again just comparing the quantiles of the observed values and the quantiles of values sampled from the this fitted distribution, again we see that most of the part of the is like there is perfect agreement, only like some very large values like we see that the it is underestimating the probability. That is basically the effect we saw here. That is why instead of while the actual frequency was 20 times, while it predicted 17 times. Like if instead of considering 150 millimeters, if we had considered an event or a threshold of say 100 millimeters or 120 millimeters, then probably we would have come closer to what is predicted by the model. But if we had considered an even higher threshold like say 180 or 200 millimeters, then probably there would have been a bigger mismatch of the frequencies. So, here you can see that even the GEV model is like slipping off, the quantiles of the GEV model distribution are slipping off near the what we can say the tail of the tail. So, like there is always the possibility of like focusing on the tail of the tail and trying to fit another distribution on it, but that is a different matter. So, this concept of extreme values is quite important in the domain of earth system science, and it has been used several times or in several research papers related to say like rainfall and climate, temperature and so on, especially in quantifying the impacts of climate change, where one of the expected impacts of climate change is that the extreme values will become more and more frequent, that is their return periods will decrease. An event that earlier could have been expected to happen once in 100 years, that is which had a return period of 100 years, now its return period may reduce to only 10 years or something like that. That means it can become about 10 times more frequent and things like that. So, there are many papers on this matter. I especially recommend you to go through this the first tutorial. So, this is some kind of a review paper, or you can consider it as a tutorial. So, this Professor Alexey Hannert, he is an expert on this extreme value theory, and there are also other experts like Professor Richard Smith of University of North Carolina and others. So, I recommend you to go through their work. So, the key points of this lecture are that the return values or the return periods they may be estimated using probability distributions. However, we may need a separate distribution for the tail of the distributions, and one such distribution is the generalized extreme value distribution. This is suitable for block maxima, and it shows good agreement with the data for maximum likelihood based parameter estimations. So, apart from we considered the GEV distribution for block maxima. Remember that we also considered the peak over threshold definition. So, in that case also there are other specialized distributions called the generalized Pareto distribution. So, you may I recommend you to go through them also. So, with that we come to the end of this topic of extreme values. We will continue on other topics of this module. Till then, bye bye.